Hello, my name is John Bereznovich. I work as an architect in the product management group of Oracle's observability and management organization. Today we're going to talk about the DB time, average active sessions, and ASH. And we're going to do that by discussing, we already learned about me, so let's go here. We're going to discuss concepts, methods, and tools. At a very high level, these are very deep subjects, each of which could probably spend an hour or a day on, but we're going to touch on the highlights and try and give you an understanding of the essence of the subject. Concepts, time is performance. So database time basically is what we understand to be time spent directly executing work on behalf of database clients. So it's really about how long are clients waiting for their SQL to be processed by the database. So we think of it as client SQL elapsed time. A more technical way to think about DB time is active foreground process time. So that requires understanding something about how Oracle SQL is processed by foreground processes, database processes. And a very abstract way to think of DB time is as the service time when you think of the database as a black box server in a larger client queuing network of servers, right? And so that's a sort of a highly abstracted way to think of DB time. So DB time is a very subtle and important concept. We model DB time as basically being in one of three large buckets, right? And the first one is being on CPU. So when the database is processing client SQL requests, you want it to be spending time on CPU because that means it's making progress on getting your answer, right? So DB CPU is vitally important because that's actual work. Besides work, database processes can wait. They can have to stall, in a sense, waiting to do work. And one of the main reasons is because it's waiting for some data to be delivered from the storage medium, and that would be time spent waiting for I/O to happen. We can't compute until we actually have the data to compute on, and that may involve I/O. So there's a certain class of waiting called I/O wait, and then there's also other wait. And we tend to break DB time down into those three big buckets, and you'll often see that breakdown. And we think of I/O wait as being necessary because the data is on some storage medium, and in order to process it at all, we have to do some I/O. So a super important concept that's kind of subtle and people often misunderstand is average active sessions. And one way to understand it is really it's the rate at which DB time spent processing database requests, it's the rate at which total DB time accumulates in the database. And the important word there is that it's a rate. It's a rate of change. So just to define it a little more formally, average active sessions is total database time divided by elapsed time over some time interval. Let's say an hour, an AWR snapshot, for instance. So it's really total database time divided by last time. And you can think of it as the rate of change of DB time over time. And that should start to sound like your high school calculus, right? It's really the time derivative of DB time. And we're actually going to make critical use of that fact when we visualize DB time. Another important property is that average active sessions is normalized, and therefore it's very comparable across databases. You can compare databases in this measure and say something meaningful about the comparison. So it's a kind of a load measure on databases. That's one way that we regard average active sessions. It's kind of the amount of pressure on the database in some sense. So ASH is an important technology that we won't go into detail about the ASH mechanism, but ASH is also kind of a conceptual thing, and that's how I want you to think about it and to work with it. So ASH is really sort of a sequence of snapshots of what's active in the database. It's a sequence of snapshots of active session state. And I really like to think of ASH as a kind of a movie of the system, of the database system, with a 1-second frame rate, right? So think of the database as a play in which there's 100 actors. But at any given time in the play, only certain actors are active on stage at a time, right? And if we took an actual photograph every second of the stage, sometimes we would see these actors, sometimes we would see those actors, but we would have a sequence of frames of the play. And that's kind of what ASH is, where the play is database activity. It's important to remember that ASH does not capture everything. ASH has so much in it that it's tempting to think of it as everything, but it's not. It's a sample every second, and a lot of things happen between samples, right? So everything that happened is not represented by ASH, but ASH does a good job of making a reasonable facsimile of what happened, and that's how we use it. Another thing that's a bit subtle but important is that ASH event timing is biased, right? So the longer a wait event takes, the more likely it'll be sampled by ASH. When sessions are in a wait event, ASH will sample those because they're considered active. And so, the sampler executes every second, but if a wait event takes 2 seconds, well, then it's likely to be, it's almost certainly going to be sampled twice and definitely going to be sampled once. Time model is an instrumentation layer whereby DB time is actually measured by little stopwatches in the code, right? And so, when certain things happen inside the database processing client SQLs, those things can actually be explicitly measured. Things like hard parsing are actually explicitly measured. And so the time model is the layer of instrumentation that handles that aspect of quantifying DB time. Couple things about time model. So it measures time in DB operations. I basically described that. It's sort of, think of it as stopwatches embedded in the code. And of everything that time model times, 2 of the most important things are the total DB time and then the total DB CPU. Total DB time is very important because it's kind of the coarsest and therefore most likely to be relatively accurate measure, because total DB time is the stopwatch that starts when the client SQL comes to the database, the foreground process, and it stops when the foreground process sends the request back, right? So that's total DB time. DB CPU is very important because it's not measured by time model, but it's actually values are fetched from the operating system. The OS instrumentation is actually doing the timing, and time model, Oracle code fetches timing, CPU timing, and then time model publishes that and bubbles it up. And so that's a very important measure. And it's important to understand that it's actually measured by the operating system and not by the Oracle code itself. And time model also includes wait event timings, even though wait event timings kind of preceded the formal time model terminology and instrumentation by a couple of releases. Time model came out in Oracle 10, and wait events have been around since Oracle 7 or so. Okay, so methods. Well, maybe we shouldn't say methods. We really have one method, and the method is shrink the time and improve performance, right? Do the same work in less DB time, and that improves database performance. And that's, exactly what the method is. Improve DB performance by shrinking DB time. So getting a little more specific, basically the first step is to quantify the DB time, measure it, and break it down into useful components. And that's what the instrumentation layers, time model, and active session history are all about. One of the critical things, and we've alluded to it at the very beginning, is, are we on CPU? Is our DB time largely spent on CPU or in IO or in wait? And the reason that's important to figure out is because those are kind of 3 very different solution spaces for how to go about shrinking DB time, which is the next step. Figure out, depending on what solution space you're in, how can you go about shrinking the DB time? Often shrinking DB time involves tuning SQL, perhaps, right? Because SQL is sort of behind all DB time. And so we often, we have a number of tools to help with this step, right? So SQL Tuning Advisor being a good example there. And then finally, it's always good, and it's often not so easy, or maybe folks just don't do it, but try to verify that the benefits you were trying to achieve were actually achieved, right? So this is just sort of a general statement about how performance tuning should be done in that sense. But so let's talk briefly about ASH math, which is really just basically estimating DB time by counting ASH samples, and where each sample represents 1 second of DB time. And so expressed in pseudocode, I often say count star equals DB time in seconds. That's ASH math, right? Count samples equated to time in seconds. Why is that? Well, because each sample counts for 1 second, because the ASH sampler executes every second. So every picture of the stage counts for 1 second of stage time, to use my analogy. A little better estimate of DB time can be made by using a column, a relatively new column, probably 12G, in ASH called microseconds per sample. And so that's really intended to say, look, rather than estimating DB time by just saying every sample is 1 second, what if samples get delayed, or what if somebody changes their actual sampling interval, which can be done. So with microseconds per sample just tells you how much DB time this sample counts for. And then we just sum those up to get total DB time. And we divide by 10 to the 6th in order to convert microseconds to seconds. And then finally, here's pseudocode for computing average active sessions, which is the total DB time, or the sum of microseconds per sample, divided by the elapsed time, which can be, estimated by taking the maximum ASH sample time minus the minimum ASH sample time. And then, of course, these would have to be rendered into the same units in order to accurately predict, compute average active sessions. So how do we visualize DB time? And this is the key thing. As a user, this is what faces you, and this is how you execute the method, right? By using some of our tools. And visualization is the key. And the core visualization that we do is of average active sessions, and we make use of the fact that the average active sessions is the derivative of the DB time. And therefore, if we graph average active sessions, the area under the curve is equal to the DB time. And yeah, I'm not going to go deeply into this graph, but to this chart, but really this chart explains why counting ASH samples is equivalent to estimating the integral of a curve, this active sessions curve, right? And so basically every series of dots is an ASH sample, and we assign 1 second delta t of time to each sample. So, the count times 1 is equal to the count. So if we add all the counts, it's kind of like adding up the area of all of these gray rectangles. And that's exactly what we used to call a Riemann estimate of the area under the curve, of the integral of the curve. So it goes back to the fundamental theorem of calculus. And this is actually the original page, the database performance page, where we first actually charted average active sessions, even though at the time, 2004, we didn't call it average active sessions. Here you can see the key chart, but the label is sessions waiting and working. The name we had for what the graph we were showing was not average active sessions, it was sessions waiting and working, which literally meant sessions on CPU working or in some wait event waiting, right? So it was a very literal name in that sense. But we realized we needed a better name, and that's when we kind of had to work out this average active sessions terminology. This was sort of a revolutionary page. Now this page, the previous page, was based on time model data, and this is the top activity page, which followed that previous page by a year, maybe, I guess, I don't know, I'm not sure how much, but top activity page is purely based on ASH math, and it basically shows average active sessions broken down by weight class, but computed over 15-second intervals, computed over ASH data in 15-second intervals. And it's just, because it's based on ASH, that enables us to do these two top lists underneath. These are detailed lists that show the top sessions and the top sequel by how much DB time, average active sessions, they're accounting for. So this is widely known and widely used and even widely copied by our competitors and even into other databases. So the usage model for the pages, these pages that show average active sessions, DB time broken down by weight class, the usage model is click on the big stuff, where the big stuff is the big color, right? And here, you know, in terms of what's interesting, these 4 giant spikes of orange stuff represent performance incidents. And it's very easy to see them because they're just large surges in DB time, and the time is spent waiting, right? So that means a large bunch of users or some one or more users all of a sudden stalled out, you know, so that's a performance incident. And then we have the associated drill downs. And the color coding is actually pretty important. I alluded to it earlier, but we try to maintain it whenever we show an activity chart. We want CPU to be green, IO to be blue, and other weight to be some flavor of orange or red. And, you know, this is sort of a Google image search of top activity, average active sessions. And you see a bunch of these different versions of top activity pages out there from who knows who on the web, right? But they're all super interesting. And without knowing any of the databases or any of the stories behind these things, you can really read a lot into these pictures, you know. This one in the middle with big red pile of time is really not having a good day at all, right? That thing's barely, probably not even running. You know, others, there's a lot of green that's very regular, or green that's up and down very regular. In some cases, there's a lot of blue. That would be IO time. Maybe Exadata is a good idea for such a database. Exadata basically being, you know, one way to shrink IO time very effectively. So this is widely used and extremely, and this has been 20 years or so that this has been sort of the state of the art in database performance observability. We also visualize DB time as via average active sessions measure in tree maps, and we kind of have 2 scopes for those. The first in the upper left here is represented the original use of tree maps in EM and even at Oracle altogether was the EM Enterprise Load Map. And that's a tree map assembled where each cell, each rectangle represents a database, and the size of the rectangle is proportional to average active sessions of the database. So you can see the heavy load, you know, this database, in this enterprise, there's a kind of a King Kong database that's basically 1/3 of all DB time. And then there's many other databases, at least several dozen. The other way we do tree maps on top of average active sessions data is by drilling down into DB time through ASH. And that's what's represented in that other screenshot, which is the Performance Hub ASH Analytics tab. And there we're able to slice and dice DB time using ASH math across all these different dimensions that ASH has. So that's a very powerful way to sort of get a view of what's been happening in your database. So let's briefly end on a quick touch on some tools that make use of DB time and actually apply these concepts and the method and try to achieve performance optimization. Hopefully you're familiar with Performance Hub, which is a real-time comprehensive database performance visualization tool that also offers connections to tools that will help you, reduce DB time, things like SQL Tuning Advisor. Here's Perf Hub. Hopefully you've seen it before. Looks not unlike its great-great-grandfather, the original performance page, activity broken down, DB time by average active sessions. Here, I think it's broken down by SQL ID, top sessions and top sequels also by SQL ID, and then a master sort of DB time selector on the top, which is a nice feature. Also, we also still have the ability to drill down using tree map decomposition. So that's where you can combine various hash dimensions and view your DB time in that context. SQL monitoring, real-time monitoring, execution diagnostics for individual SQL executions. Hopefully you're familiar with that because it's one of our most powerful and most popular tools for reducing DB time, getting a handle on how SQLs are being processed and where the time is being spent. A relatively new feature of SQL monitoring is this graphical explain plan, which is very kind of cool way to see, especially very large plans, which the SQL that SQL monitoring tends to be directed towards is heavyweight SQL, large, very expensive operations that may, in all likelihood, have complex plans. Finally, a new feature that I'm pretty excited about, Atom Spotlight. And this is basically a feature in EM and also available on the cloud in OCI Operations Insights that aggregates Atom findings and recommendations over longer time periods. Atom findings and recommendations are super expert analyses of DB time in your system, but they represent an analysis of 1 hour only, right? So they're inherently tactical in nature. And what Atom Spotlight does is it aggregates over, let's say, a week or a month, all of the findings and recommendations. It tells you what's happening most, when those are happening, how much total benefit and impact they may have. So it's a very powerful tool. The UI tends to be, fairly text oriented because Atom findings and recommendations are texty, but we compute, 3 measures: total impact and frequency, how often it happens, and then max impact within the snapshot, within any given snapshot. So findings that don't matter as much overall, but have a huge impact when they are relevant would be surfaced by such a metric. I think that's pretty much it. So thank you for listening, and we'll just flash the next slide, which has some links to others of our solution space. And that's the end of my presentation about DB time, average active sessions, and ASH.